Most weapons fail when they lose contact. A missile launches. It flies toward a target. Somewhere in that flight, it expects an update, new coordinates, confirmation, course correction. Without that signal, most weapons default to their last known instruction, or abort entirely. The AGM-158C long-range anti-ship missile does not. It was built to complete its mission after every link to its operator has been severed, after GPS fails, after satellites go dark, after the aircraft that launched it has been forced to retreat or destroyed. This is not a backup capability. It is the design requirement. Modern naval warfare operates on an assumption that no longer holds. For decades, anti-ship engagements relied on a kill chain. Detect the target, identify it, track it, and guide the weapon to it. Each step depended on sensors, data links, and continuous communication between platforms. A P-8 Poseidon might locate an enemy surface group. That information flows to a command node. A surface combatant or strike aircraft receives targeting data and launches. The missile flies, receiving updates as the target maneuvers. This model assumes the chain stays intact. It will not. In contested environments, satellites are targeted first. GPS signals are jammed or spoofed. Data links are disrupted. ISR platforms, the aircraft and ships that provide targeting information, operate at risk. They must stand off or withdraw to survive. Communication between the shooter and the missile becomes intermittent, then impossible. Legacy systems were not designed for this. The AGM-84 Harpoon, the Navy's primary anti-ship missile for 40 years, functions well in permissive environments. It requires accurate target coordinates at launch. It flies a pre-programmed route. If the target moves significantly, or if initial coordinates are imprecise, the missile's onboard seeker has limited ability to adapt. It searches a defined area. If the target is not there, the mission fails. The question became unavoidable. What happens when the kill chain breaks halfway through an engagement? The answer is LRASM. The AGM-158C LRASM is a subsonic, low-observable anti-ship cruise missile. It can be launched from aircraft, B-1 bombers, FA-18 Super Hornets, and from surface ships via the Mark 41 vertical launch system. Its range exceeds 200 nautical miles. Exact figures remain classified, but the design philosophy is clear. Standoff distance matters because the launch platform may not survive close engagement. It does not fly fast. Speed is not the solution here. Supersonic missiles are visible. They generate heat signatures. They can be detected early and engaged by layered fleet defenses. LRASM flies low and slow, using stealth shaping and radar-absorbent materials to reduce its cross-section. It approaches below the horizon, minimizing detection range. The warhead is a 1,000-pound penetrator. It is not designed for spectacular surface effects. It is designed to penetrate a ship's hull and detonate inside, targeting critical systems, propulsion, power generation, combat systems. A ship does not need to sink to be removed from the fight. It only needs to lose the ability to maneuver or defend itself. But the warhead is not what makes this weapon different. What makes it different is what happens after launch. LRASM carries a multi-mode sensor suite. It has a passive radio frequency sensor and an imaging infrared seeker. Both are passive. They do not emit. They listen. The RF sensor detects emissions from the target, radar, communication systems, electronic warfare equipment. Every modern warship radiates. LRASM uses those emissions to refine its course. It does not need to be told where the target is. It finds the target by what the target does to defend itself. The infrared seeker provides terminal guidance. It detects heat signatures from a ship's exhaust stacks, gas turbines, and other thermal sources. In the final approach, LRASM correlates infrared data with expected ship profiles. It is not looking for a ship. It is looking for this type of ship in this formation with these characteristics. Onboard processing allows target discrimination. The missile can distinguish between a cargo vessel and a combatant. It can identify higher value targets in a surface action group and prioritize them autonomously. If it detects a cruiser, a destroyer, and a supply ship, it will select the cruiser. If that target is obscured or already engaged, it will shift to the next priority. This is not artificial intelligence in the speculative sense. It is a decision tree based on sensor data, preloaded threat libraries, and engagement logic. The missile was told what matters before it launched. It executes that guidance without further input. Navigation does not rely on GPS. LRASM uses inertial navigation updated by terrain referencing over land and correlation with known coastal features. Over open ocean, it integrates inertial data with passive sensor updates. If it detects an emitter at a known location, it corrects its position estimate. If it does not, it continues on inertial guidance and adjusts as new information becomes available. The missile plans its own route. It can avoid known or detected threats, an enemy surface group, a radar field, a patrolling aircraft. If it detects an air defense radar, it can alter course to minimize exposure. This is not evasion in real time. It is threat awareness and course adaptation. It sea-skims. Flight altitude is typically under 50 feet. At that height, radar horizon limits how far the missile can be detected. A ship-based radar might not see LRASM until it is within 20 miles. That gives the defender minutes, not tens of minutes, to respond. Every technical choice serves the same purpose. Allow the weapon to complete the mission when the operator cannot help. Fleet air defense is built on layers. Long-range SAMs engage threats at distance. Medium-range systems create a defensive zone. Close-in weapon systems provide last-ditch protection. The entire structure assumes early detection, tracking, and engagement. LRASM compresses that timeline. By the time a defender detects it, much of the engagement timeline has collapsed. The missile is low, it is slow, and it is already inside the medium-range defensive envelope. Intercepting a low observable sea-skimming target is harder than engaging a high-altitude or supersonic threat. Radar lock is inconsistent. Fire control solutions are brief. More importantly, LRASM does not require centralized command to function. A traditional anti-ship strike involves coordination, multiple aircraft, multiple missiles, synchronized time on target. If one platform loses communication, the strike degrades. LRASM allows distributed operations. Individual launch platforms can engage independently. The missile does not need to know what other missiles are doing. It finds its own target. This enables the distributed maritime operations concept. Instead of concentrating firepower in a carrier strike group, the Navy disperses assets, surface combatants, aircraft, even unmanned platforms across a wider area. Each platform can prosecute targets independently. The enemy cannot destroy the kill chain by targeting a single node, because there is no single node. In anti-access, area denial environments, regions where adversaries deploy overlapping sensors, long-range fires, and integrated air defenses, LRASM allows strikes without penetration. The launch platform does not need to enter the threat envelope. It can fire from standoff range and withdraw. The missile handles everything else. This is not a minor capability improvement. It is a structural change in how naval fires are employed. Some analysts describe LRASM as a smarter harpoon. It is not. Harpoon is a terminal homing weapon. LRASM is an autonomous mission system. Harpoon requires accurate target data and operates within a narrow search area. LRASM conducts its own search, discrimination, and engagement. The difference is not incremental, it is categorical. Others raise concerns about autonomous weapons. The argument is familiar. Removing humans from targeting decisions is dangerous, prone to error, potentially escalatory. The counter-argument is operational reality. LRASM's autonomy exists because the human may not be reachable. If communications are jammed, if satellites are down, if the launch platform is under attack, the operator cannot intervene. The missile must function without guidance, or it must abort. Aborting guarantees mission failure. Autonomy provides a chance of mission success. The missile does not decide whether to launch. A human does. The missile does not decide what constitutes a valid target. A human defined that before launch. What the missile decides is which target in the assigned area matches the criteria it was given. This is not recklessness. It is necessity. Human-in-the-loop control is safer when the loop is intact. When the loop is cut, dependence on that loop becomes a vulnerability. Independence is a response to adversary capabilities. Jamming is not theoretical. GPS denial is not speculative. Adversaries have demonstrated these abilities. Weapons that depend on continuous external guidance are not reliable in that environment. LRASM was built for that environment. The assumptions behind this missile are worth stating plainly. It assumes GPS will be unavailable or unreliable. It assumes the launch platform may not survive long enough to provide updates. It assumes ISR assets will be degraded, delayed, or destroyed. It assumes centralized command will be disrupted. It assumes the operator will not have perfect information and may have no information at all after launch. These are not worst-case scenarios. They are planning assumptions. The weapon was designed to succeed when everything else has failed. Not because failure is acceptable, but because failure is expected. The most independent weapons are not built for confidence. They are built for uncertainty.